question 3 then is asking us first of all about gas chromatography, and it just asks the very general question why compounds may have different retention times in gas chromatography. So this is just asking a very general question. You shouldn't be talking about specific types of intermolecular forces or about things being more or less polar, because we've got no information about what kind of stationary phase we've got in the gas chromatograph. So we just are answering this question in completely general terms. The important thing is that you don't get it mixed up with TLC. So TLC is about adsorption to the stationary phase, because you have a solid stationary phase and things stick on the surface of it, which is what adsorption means. In gas chromatography you have a liquid stationary phase, so it lines the inside of the column. But because it's a liquid, things don't just stick on the surface of it, they dissolve in it, and that's what you should be talking about. So the simple answer is that if substances have different solubilities in the stationary phase, then those that are more soluble will take longer to get through the column, because the more time they spend dissolved, the less time they're spending actually flowing in the gas and making progress through the column. So the simple answer is that the more soluble a substance is in the stationary phase, the longer its retention time will be. Now part B is asking us about a reaction which has been followed by using gas chromatography. So these are a series of gas chromatographs of samples taken at the very beginning of the reaction, before the catalyst was added, it tells us, so before any products could have been formed, and then after 4 minutes, and then after a significantly longer time. And we just really asked to figure out which substance is which, or what the structures of the substances are. So we'll worry about the reaction in a minute. But the first thing to be really clear about is that this one at the top is taken at the very beginning, before there can be any products formed, because no catalyst has been added. So these peaks must be the reactants. That's really important to recognise. So we can narrow it down straight away, because we know that we've got 2 peaks there, so there must be 2 reactants, and it tells us what the reactants are. So we've got nitrobenzene, which is that. NO2, remember, is a nitro group, and we've got 1,4-dichlorocyclohexane. So there's a cyclohexane ring, and 1,4-dichloro means that it looks like that. So those 2 substances must correspond to those 2 peaks, but the question is which one is which. And the way we work that out is to notice that in the question it says that the nitrobenzene was in excess. That's underlined in the top line to draw your attention to it. If it's in excess, it means there's some of it left at the end. So it's easy to tell which one is which, because you can see that at the end of the reaction there's still some of this substance, which is the 14.2 minute one, and there's none of that one. So that must be the one that's in excess, so we can say that the 14.2 minute one is nitrobenzene, because it must be a reactant since it's there at time 0, and it must be the one in excess because it's still there at the end. This therefore is the other reactant, which is 1,4-dichlorocyclohexane. Sorry, no, be very careful not to do what I was about to do, because you get in the habit of putting those circles in the middle. But remember, if it's cyclohexane, there is no circle there, so that's that compound. So now we've got to work out what these other 2 peaks are. And so you can see this one is a substance which is made first but then disappears again, whereas this one is the final product at the end of the reaction. And we've got a bit of extra information for that one, which is that the M/Z value for the molecular ion peak, which remember is equal to the MR for the compound, is 326. So we have to think, well, what do we expect to happen? And the big clue was that it told us that we had an aluminium chloride catalyst. That should immediately tell you it's a halogen carrier and make you think, oh, this is a Friedel-Crafts reaction. So Friedel-Crafts is an incredibly important reaction, because it's a way of making new carbon-carbon bonds, which has a special importance in organic chemistry. So you're going to get lots of questions about Friedel-Crafts reactions. So you need to know it. And it's very easy to figure out what happens in one of these reactions, because basically in the presence of that aluminium chloride catalyst, where you have a chlorine in an organic compound, you replace it with a benzene ring. And it's as simple as that. So it's easy to work out what the structure of the product is. Now, the complications here. First of all, we've got 2 chlorines, and we're going to have to worry about that. Secondly, we've got this NO2 group on the benzene ring, and we're going to have to think about where will the substitution happen relative to that one. So let's deal with the NO2 group first. What you need to know, because it won't tell you this is something that you're supposed to specifically learn, it's on the syllabus, is that that is an electron withdrawing group. And that has 2 important effects. First of all, it lowers the activity of the ring because it pulls electron density out of it, decreases the electron density, makes it less attractive to an electrophile. That's not relevant here, but also it directs substitution to the 3 position. 3 and 5 if it substitutes more than once, but 3 in the first instance. So we know that we expect substitution to go there. So what's going to happen is, if we just redraw this so it's that way up, keep doing that, what's going to happen is that we're going to substitute that chlorine by forming a new bond to the benzene ring instead. So we expect, first of all, to make that product. However, that's not the final product, because we have excess nitrobenzene, and so this chlorine can react as well. So what we're going to expect is that this one will be formed first, so let's just draw it again. But that if we wait a bit longer, this chlorine will get substituted too by another nitrobenzene, because we know the nitrobenzene was in excess, so there's enough of it for more to react. So that chlorine too gets substituted and replaced by a new benzene ring. And again, sorry, I put that NO2 in the wrong place. Let's get this right. They've got to be at the 3 position. Right, so both of the nitrobenzenes substitute at the 3 position. So that's what we expect to get at the end, and if we check out the MR for that compound, it does indeed equal 326. So what we can say then is that this one is the final product, because it makes sense, it's what we would expect the final product to be, and it has an MR which is consistent with the molecular ion peak in the mass spectrum. And we're going to think that almost certainly this is the other compound, which is made first, because it's obviously not there at the beginning. You make some of that, but then as soon as that chlorine reacts, it changes into this, so it disappears again, and that's what you're seeing here. So this peak at 19.9 minutes comes from that one. And that fits the data. Now, it didn't ask you for explanations, so you didn't need to waste time writing your reasoning. Check the question. If it says give your reasons, then give them, but it actually doesn't. It just asks you to suggest the structures. So we've got the 2 reactants, this product that's formed first, and then this one at the end. One thing you need to be slightly wary of is you might be tempted to think about the intermediates in these reactions. So remember these kind of things where you have carbocations, which would be intermediates in these substitution reactions. Those kind of things are very highly reactive intermediates. They're only going to exist for very short times. So you can't detect them in gas chromatography, because remember, it takes maybe half an hour to run a gas chromatogram. So don't be tempted to think, oh, it's an intermediate of that kind. What we're talking about here is a compound, a stable compound which is formed, but which then reacts again. And that's a complete answer.